Welcome dear students to the lecture series of automata theory. The topic that we are going to learn today is about construction of a regular grammar. When we say I want to construct a regular grammar, it can be of two types. It can be either left linear grammar or a right linear grammar. To know what is a left linear grammar and right linear grammar, please check my video given in the comment box below. I have provided the link there. Okay, so now if the question I'm just reading out, construct a right linear grammar for all the strings over A and B that start with two or more A's followed by three or more B's. If this is the question given to me, okay, how will I proceed with it? First of all, let us try to write down the language that is acceptable by this type of a question. Okay. So here is the language where I have more than 2 number of A's followed by more than 3 number of B's. So if we see properly, we can say 2 A's and 3 B's is a compulsory. Other we can have any extra numbers of A and B. That is not a compulsory thing. Okay. So how can I derive the grammar for this? So let's derive it step by step. Very first we'll assume that every grammar start with a start symbol or start variable. So we assume the start variable to be S. Now here we have written that we begin with the start symbol S and to accept the string that are starting with 2 or more number of A's. So just we'll write down the first of all the grammar to accept the strings which are starting with exactly 2 number of A's. So how do we go ahead with that? We'll first say S is a start state, gives you one small A terminal, okay, now followed by a capital letter A, say for example. So here we are reading one number of A. Now once we go to A, from A I will read one more A and I am going to another variable, say for example B. So here what I'm doing is I'm going from S to A and A to B, and there when I reach at B, I am reading 2 number of A. So I can say this is grammar to read 2 number of A's. Now to generate more additional number of A's, if a user wants to take, he may take, otherwise he may simply ignore. So I am right now at state B. So from this variable B, I can say if you want to have any additional number of A's, you can take and again go back to the same thing. So here it is going to be only, that is in looping. So if you want, you can take, otherwise you simply ignore that. So to make this, I can just make use of automata, okay, and I can make an NFA just to understand how I'm proceeding with it. Can I draw a automata for this and say for example, from S, I'm reading a small a and going to A. From A, I'm reading a small a and going to B. At B, I am giving a self loop which is allowing me to read A and go to B many times. So when I say S on A goes to capital A, I have written this rule. A on small a goes to B, I have written this rule. B on self loop on A goes to itself. So B on A goes to itself. So now looking at this, I can say I have done with the strings that are accepting 2 or more number of A's. Now after A, I should be accepting B because A is followed by B. So how do I do in this case? That is, if I just look at this diagram, so I can say, yeah, I have to add more number of B's after this. So I should have minimum 3 number of B's. So can I say I make an FA like this? So 3 number of B's, okay, and first B we are going to C, second B we are going to D, and third B we are going to E. And after that you can have n number of B's if they want to come. Okay, so I can just write down the statements in the grammar line. So here I can write the grammar in this way. B, to accept 3 number of B's. Okay, right. Currently I am at B. So B on reading small b goes to capital C. From C, again on reading small b, I can go to capital D. And from D, on reading small b, I'm going to capital E. So here I'm making sure that I'm reading exactly 3 number of B's. Now to have more number of B's, which is optional, I can write another grammar. So I can say to generate the additional number of B's, currently I am at state E. So E on reading B goes to E only. That is a self loop where we are just allowing them to give more number of B's if they want to. Okay, so this is the grammar that I have written. But if you observe, the grammar is in right linear grammar pattern. Why? Because right linear grammar says what? So let us just revise in about what is a right linear grammar. So, right linear grammar is something where we have any rule where we have this right hand side of the rule. Yeah, this is the right hand side of the rule. So, in right hand side of the rule, the non-terminal that is coming, non-terminal is nothing but a capital letter. It should be the rightmost symbol. Yeah, so now here capital letter is nothing but A. So, A should be the rightmost symbol. Yes, so A is the rightmost symbol, and I make sure that all the production rules that I have in my grammar, everywhere the capital letter that is coming, say for example, this one, are all on the rightmost symbol. So if you look at our grammar, we can say, yes, we are following that because here in each grammar, the rightmost symbol is there on the capital symbol is there on the rightmost symbol. Yeah, and that's why the given grammar that we have written is a right linear grammar. Now every grammar is ending with the capital letter, that is a non-terminal. So if we just try to derive a string from this grammar, we will never stop because it is continuously going giving us another capital letter or another non-terminal. So we, to accept a string and to stop, we need some production rules which are stopping at terminal symbols, means which are giving only terminal symbols. So here in this grammar, when do we say we accept the grammar? When we reach E, we accept the grammar. So I have to do one thing. I have to make a final state here. Okay, and I can say E on reading epsilon goes to final state. Okay, so for this particular type of line that I have added in my NFA, what can I write in my grammar? So I can say in my grammar that E gives epsilon. That's it. You should not be writing capital F here. Okay. So I'm just writing E giving epsilon. So whichever transitions that are going to final state, I'm simply writing it with the that terminal symbol only and not with the final that non-terminal. Okay. So here E giving epsilon is the production rule which is giving you terminal and which is giving you allowing you to stop your string, and there the grammar is now complete. So this is the solution for the given grammar. In this, whatever I have written in the blue color, you can write mention as the answer. Whatever I have explained you in using this red color and green color is just for understanding purpose. If you skip or avoid writing this, that is also okay. I hope you understood. So can we take a next example now? Okay, now consider we have given a question. Construct a right linear grammar to accept the binary strings containing at least two ones. Okay, now let us first write down the language for this question. So I can say it accepts the strings where we have exactly two ones coming as a minimum possible string. Then I can have any number of zeros coming. It can be coming in between, after, or at the end of the one. Or I can have minimum two ones, maximum any number of ones, and there is no absolute limitation on zero coming how many times, not at all occurring. Or I can have only string with the all ones as well. Okay, so this is what the different types of strings which are acceptable by this grammar. So many times you get this question, how do we find the solution very easily? Yeah. So there is a trick. Now, if there are some questions for which we can easily construct the regular expression. अभी ये क्वेश्चन के लिए हम लोग रेगुलर एक्सप्रेशन बनाना इज वेरी इजी सो इफ यू मेक अ रेगुलर एक्सप्रेशन एंड देन वी ट्राई टू कंस्ट्रक्ट द ग्रामर द थिंग्स आर गोइंग टू बी इजी फॉर अस okay so let's try doing that so how can I write the regular expression for this I can say regular expression is equal to say for example any number of zeros and ones followed by 1 again any number of zeros and ones followed by 1 and then any number of zeros and ones. That means I'm making sure that I'm taking exactly two ones and before that or in between or after that it can be any number of zeros and ones. Okay, so now if this is a regular expression, now I will try generating the grammar using the regular expression. Okay, so let us start. So now we'll consider S as a start symbol and I can say in the beginning I have to consider this part of the regular expression. That means I should be able to read 0. So S can give you 0 and here I have got a closure. That means 0 can come many number of times. So whenever there is something which is coming many number of times, I should be giving the same symbol which I am starting with. That's why S giving 0S. So many times 0 you can take. Then after that I have another rule that it allows me to take 1 coming many number of times. So I can say 1s. So 0 plus s closure, 0 plus 1 closure can be written with these two productions. Okay, so I hope this is clear. Now after this I want to read this 1 which is a compulsorily one number of 1 should be coming. Now that is a compulsory thing, that's why I should be going to another state. So to accept exactly one occurrence of 1, what I am doing is S on 1 goes to A. Now this is something compulsory, so that's why I am not going to self loop. I am going to some next non-terminal symbol A. And here what I make sure is I am reading this 1 and then only I am going ahead to A. Okay, now I am supposed to read this next closure of 0 plus 1 star. Okay, so I am just writing to accept 0 plus 1 closure at A. Means I have already read one number of 1 and now I can have any combination of zeros and ones coming in between. Okay, so to allow that what I am doing, so this particular thing in the regular expression, what I am doing now is I am saying I am saying I am at A right now. So A on 0 goes to A and A on 1 goes to A. So here I handle this 0 plus 1 closure coming second time. Okay. Now again there is this one number of 1 coming exactly once. So on reading second number of 1 I should be going to next symbol. So I am just writing to accept second occurrence of 1. I am going from A to B on reading second time 1. So here I just make sure when I reach B I have read exactly two number of 1s. But after that also I can have any combination of zeros and 1s coming. So another closure I should be handling. So I am just writing to accept 0 or 1 closure after reading two number of 1s. So now I am at B. So I can say on 0 it goes to B, on 1 it goes to B. Okay. Now we are done with the regular expression. Our regular expression is complete. So again I will just check once again. All my rules are in right linear grammar properly. Okay, because the capital symbol is coming as a rightmost symbol. And that's why I can say my grammar is a right linear grammar. And it's a perfect grammar. But here there is no such production rule which is stopping at a terminal symbol. But at the end of this regular expression, once I complete a string, I should be stopping here. So to stop, what I am doing is from the last state, that is B. So I am adding one more rule here. From the B, I am going to epsilon. So here what I am writing is B goes to epsilon. So though if we reach B, then only we can stop. Because at reaching B, we make sure we have read exactly two ones. I have minimum two number of ones. And then I can allow the string to stop. So this is my final grammar. So after deriving this grammar, I can just write it all together as one set. Yeah. So at the end, I can write my grammar like this, where G is equal to VTPS, where V are all the variables or the non-terminals in my grammar. So those are the all capital letters as A, B. Terminals is a T, that is zeros and ones, which comes in my final string. S is a start state. So here I am using S as a start state. And P is a production rules, a set of production rules. So I'm writing all the production rules all together that I have just derived in my grammar like this. So can I, how many production rules are there in my grammar? We can just count them. That is 1, 2, 3, 4, 5, 6, 7, 8, 9 production rules are there in a grammar. So with this we are done with the answer. Thank you for watching this video. Please do watch the next other videos as well to find more examples in the same. Thank you.